Okay, it's 1 o'clock, so we should get started. So today we're really pleased to have Yikun Wang come to give a seminar. She obtained her PhD from the University of Chicago in 2021, which is now a postdoctoral fellow in particle physics phenomenology at Caltech. She's interested in a range of things, including physics beyond the standard model, collider phenomenology, and dark matter. And today she's going to talk to us about Axion detection with optomechanical cavities.
Right. Thank you so much for the introduction. So it's a pleasure to be here to talk about this because there are many groups thinking about optomechanical system here at Wright Lab. So this is a theory proposal stage. So we're considering what if it's interesting theoretically. Of course, this depends on eventually the actual experimental realization that we're actively discussing with Jack Harris group here. And hopefully there can be a concrete experimental proposal. So here is the archive number of the theory part of the paper, and this work is in collaboration with Clara McGree. She's a postdoc at Caltech. I think she's moving to CERN, and Catherine Griff. This will be a cute way to detect axion, and specifically we're thinking about axion dark matter. So we're talking about dark matter detection. So I just want to show you very quickly where we're standing about axion today. So we are going to assume our axion is dark matter. So I will be using these two numbers, the local velocity of dark matter and also the mass density of dark matter throughout the talk and the calculation. And in case of detecting dark matter, we like to think about it along the mass axis because the dark matters will behave very differently, depends on where they are. Of course, I'm giving you a couple of examples for theory motivations of dark matter that also depends on the mass range. So what we're going to talk about today is this ultralight frontier. We like to call it wavelength frontier as well, because with this very tiny little mass here, a very rough range from 10 to the minus 22 eV to 1 millieV, the dark matter will behave like waves. So how waves, so we'll be talking about oscillating photonic field here, and so how such oscillating light fields can be dark matter candidate is one concrete example is given by this misalign mechanism, still the most popular mechanism. Basically, the oscillating field will be inducing in the early universe when the Hubble constant is cooled down below the mass of this field. Let's call it A, because we're talking about axion today. Of course, this was actually proposed to think about QCD axion, which is a solution to strong CP problem. That's another problem in particle physics to make it a dark matter candidate. So another feature of dark matter in general is it couples very weakly to the standard model, our visible sector. And the natural way to think about this is if this dark matter candidate, this new dimorphism, is associated with a heavy scale, the scale that's much heavier than our standard model one, which I call F of A. So this is the energy scale, can be much higher. And so this, and then the coupling between this new field A with our visible sectors, phonons, fermions, gluons, and also photons, that's the FF term here, will be naturally surprised by this high scale. And if you think about these two features, that makes the axions a natural candidate to be dark matter in this mass range because it has both features. So the QCD axion was actually first proposed to solve the strong CP problem. And then people realized it can be very well a dark matter candidate. And for the strong CP problem here, next feature is the mass of the axion. Well, it's theoretically it's more complicated. That's induced through mixing with the pions. But very naively, you can think about it as surprised by the relative scale between the QCD and the new UV heavy scale F of A here. So that naturally predicts the very light axion mass. At the same time, if you look at the coupling I was writing down earlier, the coupling is also surprised by this scale. So this simple estimate or naive estimate shows you a nice relationship between the coupling of the axion with the visible sector to the mass of the axion. And that will be clear from the plot I'm going to show you. of course, other than QC the axion particles like as pseudoscalar of some symmetry are naturally light. So that's why we also talk about axion-like particles. And for example, like this kind of particles are well motivated in string theory. So they are also theoretically interested. But for general axion-like particles, you do not have this very specific correlation between the coupling and the mass, but you can still make projections, make predictions on the axion parameter space plot I would like to show and being kind of manipulated by the end. So we're talking about axion coupled to photons. So that's the Lagrangian I'm showing there, and it's actually quite natural to think about seeing axion through this photon degree of freedom because we have very good control and experimental sensitivity to photonic degree of freedom or E and Fs. And this is the current knowledge we have about the axion to photon coupling as a function of the mass of axion. So the next relation between the coupling versus mass for QC the axion is shown with this orange band here. So you can see it's a linear relation, and of course, depends on how you write down your UV completion model. The slope of this relation changes slightly. That's why you have a band here. And there are two benchmarks we like to refer to. Those are two UV completion models, KSVZ and DFSZ. So those we always refer as the benchmark from theory prediction that we would like to catch, we would like to probe. So other than that, this is the model part, theory part, and then we already have a lot of knowledge on where axion does not exist. So for example, we have a bunch of astrophysical and cosmological bounds here. And we also have some direct detection, which are broadband up here. But as you can see, the ones that are currently touching the QCD band are all centered around this mass range here. And this bunch of experiments, most of them are called the heloscope. So this is the heloscope is naturally a narrow band detection. That's why you see like each experiment are only probing the axion mass within a very small range. And also you notice that all of them are around this macro EV to maybe 10 macro EV and a little bit above mass range. And that is not a coincidence, or it's not what we decided to randomly put our experiment there. It comes with the design. It comes with the feature of the designing of such heloscope experiment. So here is just a very quick summary of what kind of axion searches we're currently thinking about. And today we're going to talk about so-called axion electromagnetism. Basically, it's axion talks to photons. And the most famous design were most of the direct, the very good sensitive experiments are called a heloscope that was proposed in many years ago. So here's the basic idea of this type of experiment, which is simple. I like to use Faraday diagram. So it's simply a photon, a 2-to-1 process where the axion, which is dashed line, will convert one photonic degree freedom into another photonic degree freedom. For example, in 80 mass, and also answer his that here. So the initial photonic degree form is actually a static magnetic field because you can make it very strong. And then the axion will convert that magnetic field into a photon. That's your signal photon. That's what you see in your detector. Either you see it through like observing the power, or you see it through like single photon detector. So so naturally this coupling is super small, as you can see from the previous plot. That means this conversion process is not so efficient. So your signal naturally will be very small. Of course, we won't be able to see a super small signal, and the trick we use to enhance this signal is putting the outgoing photon to be on resonance of some resonator system. For example, optical cavities or LC circuit can also do that, and that brings the problem. So you can enhance the rate so it's large enough to be observed, but you need to make your outgoing photon to be on resonance of your system. And by simple kinematics, you figure out the outgoing photon will have the frequency more or less of your axion mass. And then that means you need to match your axion mass into your size of your system. Let's talk about Caltech. So that is why most of the heloscope are in micro EV range, because you think about it, if you go to higher frequencies, that means you need to shrink your size of your cavity. to make this true. And once you shrink the size of cavity, the enhancement rate for this process becomes smaller. So that means at some point of the higher mass, you won't be able to see the enhanced rate because the size of your system becomes smaller and smaller. So that's the problem with high axial mass. For low axial mass, in principle, it goes well. I can just make my detector larger and larger. It will match this as well as will help my rate. But there's a technical problem. How can you make a cavity that is 10 kilometers, 100 kilometers? That's what you need to prove lower and lower axial mass, right? So for lower axial mass, because of this, there is this technical or realization problem. So that's why if you think about all these telescope experiments, they are mostly around microwave. So now we can't just sit there and say, okay, we want to look at this mass ring. We still need, because we haven't seen Axion yet, and there is a broadly open blank space here on theoretically motivated, but haven't been seen by any experiments. So we need to explore those regions. And of course, there are many smart people out there think about what is a way out to break this scaling. And here I'm giving a couple of examples. So for example, people think about plasma, basically photons of plasma match. People think about dielectric, so you stack different materials together, so you can match into two different modes. And I think abracadabra is using some lumped elements design. So there are ideas there, but it's all like in the proposal phase, and everybody comes with a problem. So what I'm going to show you today is a new idea that is different from any of this to solve this problem. And the solution is quite simple, is to introduce another degree of freedom into the system. So here, that's our hero today, the phonon. So, or you can think about acoustic wave or mechanical mode in your system. So essentially, you just bring a 2-to-1 process to be a 2-to-2 process. So you have your initial photon, Axion comes in, and that will, of course, produce the signal photon that we're going to see today. And at the same time, it will kick off the phonon. So the phonon is there for two purposes. The first one is to solve the dependence on the cavity side, because the dependence on cavity side is simply kinematics, right? You want the photon to take away the energy of your axion. That's why you need to match the photon energy into the axion mass. But here we have additional degree freedom, the phonon. So eventually you will see that the phonon will take away most of the momentum of the photons. It will take away part of the energy of the axion. So it helps with the kinematics, and eventually I no longer need to match the axial mass into the cavity side. That I'm going to show explicitly, but I want to give you a head up. And the second feature actually is very cute, is because I can prepare the phonon to be in a very coherent state. So I'm talking about multi-phonons instead of single phonons, thanks to our friends in experiment, they can do that. And that number of phonons can help to increase your rate. So not only you get a coherent enhancement from the photon in a cavity mode, we're still talking about the optical cavity, you can get coherence from your phonon being a coherent state, and that helps with the rate. So we actually get two benefits from introducing a single degree of freedom. Okay, so this is kind of a summary of what we're trying to solve and the way we solve it and what are the benefits. So now I will go to the details of how exactly this works. Okay, so from this slide, I'm going to talk a lot about optomechanics and introduce a lot of concepts. I think we have a diverse audience here, so please stop me whenever I'm not explaining the concept clearly, or please bear with me if you're super familiar with this. So our system starts with optical cavity, and what we know about optical cavity is that we'll confine lights or confine optical mode. So here I have a cavity of the size of the lens, so you need to match the boundary condition for your optical waves, and that gives you resonance wavelength of the optical waves, which is just the half wavelength need to be integer fraction of your length of your cavity. And that naturally gives you a frequency of the optical mode you can host in the cavity, which is again integer number of times its inverse size, which we call spectral range frequency, like that's used throughout the talk. And but the cavity is not perfect. So it means that your mirrors can't reflect lights infinite time. Eventually, because of the imperfect mirrors, these lights will leak out or it will decay. So that is why we have a concept of optical width of the modes. So your width, sorry, I forgot to say that. Let me go back. So it's helpful to look at these modes in the frequency range because that's where our signal will be identified. So in the frequency is optical frequency, your optical resonant mode will just be localized at different resonant frequencies. But of course, because the effect I was talking about, you can't get away with monochronic light. This will be decay. So I would like to think about it as a decay term or damping term of electric field or magnetic field of these modes. So that's be reflected into the frequency. Section we're seeing is basically instead of perfect delta function, localize a certain frequency, you're looking at a little bit broadened mode. So we described it with Lorentzian, which is basically for a transform of this guy. So the actual optical mode will be described by this Lorentzian shift in the frequency range, which comes with the half width at the full height. We call it kappa. So kappa is the decay. It's a decay rate, or it's the lifetime of the optical mode inverse. So it's a quantity that comes with the energy, dimensional energy. Okay. So this is the second concept I would like to introduce to describe the modes, the optical modes. And last one is actually describing how strong this mode is, or like amplitude of this mode. And we would like to describe it in case, like quantized language, which is the photon population number. So basically you do a second quantization of your electric EMF field, and you end up with the photonic freedom. And the useful quantity to describe how many photons or how large your mode is the photon number. That of course depends on the laser power you use to drive this system. You use to drive the optical mode into the system, and it also depends on how long this mode will live in there. So that's why your bit here kappa goes into the expression. And this bit is a little bit detailed. But basically, it's a constant. If you're not injecting your laser exactly at the resonant mode, if you have a slight mismatch between laser frequency, which is the fundamental resonant frequency, then you will on this photon number. But for simplicity, we're always assuming that the optical modes we're dealing with are on resonance with the cavity, so we don't have this suppression. But in reality, that may happen. Okay, so these are very basic description, and this has actually been used exactly at heloscope designs. That's when we're talking about resonance. And just a summary, I introduced 3 quantities to describe optical modes in the optical cavity. And now I would like to introduce my hero today, the next element we want to evolve, which is sound or mechanical mode or vibration of your material. So what happens is the mirrors of your cavity not only can confine lights, it will also confine sound. So it will reflect the mechanical waves as well. And for example, I can drive a mechanical mode into the cavity with, for example, a piezo. And of course, because I'm looking at the density fluctuation, that's your mechanical mode. That's why we need to fill up the cavity with material. So I'm thinking just put the material there. And in this work, we are assuming superfluid helium. But of course, you can get away with other material. They come with different properties. So that's something to be explored. But we're assuming superfluid helium. So now I can use exactly the same quantities to describe the mechanical mode, almost identical to the optical mode. So I have some resonance condition because the wavelength of the mechanical mode also needs to match in the cavity side. But because of dispersion relation, the frequency of your mechanical mode comes with the additional factor of speed of sound. And the speed of sound is much smaller than speed of light, which we assume to be 1, which is about order of 10 to the -6. So this is a very nice feature that will be useful in kinematics. And of course, the mechanical mode won't be infinitely long life, so it will decay, and you have a similar quantity, which is the decay width, or inverse lifetime of mechanical mode, which is again suppressed by the speed of sound. So that means your mechanical mode is naturally much more narrower than your optical mode. And lastly, we want to quantify what is the size of your mode. So how many phonons, if you do quantization of the density fluctuation, you end up with phonons. And then we use this phonon number to describe how large the mode is. And so unlike the optical mode, you can kind of use your laser power to quantify it. It is a little bit hard to describe how powerful your PSO is. So here in this work, we use the phonon number as a free parameter, and then we'll be asking the question to our experimental friend how many phonons you can count in the cavity. So we're treating this as the free parameter. Okay, so I have introduced the two elements here, the photon and the phonons. And the good news for us why there is structural proposal is because these two modes talk to each other. So this is the so-called optomechanical coupling. So they talk to each other in the way that shouldn't be surprising to you, because the EM field will talk to the local density of your material, right? And that the coupling is given by the polarizability of your material. So this is my original Hamiltonian, and I like to think about the quanta. So I can quantize both the optical modes, the EM waves, and the meta mode. So the quantization of this density operator is our phonon. And with that, I end up into this same Hamiltonian written in a slightly different fashion. So I will have creation and annihilation operators for my photons, and I have creation and annihilation operator for my phonons. So this is kind of linear coupling. So you'll have two photons here and a J, and you'll have one single phonon here. So either created or annihilated. And then there is a data coupling G naught. So G naught is the literature quoted optomechanical coupling, and you should say that will know about observability and also a lot of other things that I'm written down here. So just do the duration, and you'll figure out the G naught depends on functional properties of your material and also optomechanical mode. For example, it depends on dielectric of the material, so that's your polarizability part. It depends on the frequency of both the optics and the mechanics. Depends on the speed of sound. Depends on the density of your material. Depends on the mode volume. The mode volume is similar to the volume of your cavity, but not exactly. So the mode volume scale as cavity length square times your wavelength of the mode. But the important factor I want to tell you here is the last one. It's called overlapping factor. So this is basically, well, from optomechanical literature, it's how well your optical and mechanical modes overlap with each other. So it was a little bit hard for me to understand in the beginning at the particle physics, but later I immediately realized this factor is just our momentum conservation in free space. So that's my favorite part. So when you do the duration, you think about the cavity, so it's a finite volume. But if you take the cavity to be infinitely large, so you're in free space, and what that gives you is a momentum conservation delta function. And you can see that as well, because the single function, if you take your size of the cavity to infinity, it becomes a delta function. So I always like, for simplicity, I will assume that the overlapping factor is 1. That means I'm imposing momentum conservation in duration, but in reality, it can be violated because you're in a cavity environment, you're not in free space. So I have introduced everything for the complementary coupling and our participants here, the photons and phonons. And I would ask the question, what will happen for a cavity with this interaction? Of course, Axion is not there yet, but it's very important to say how these degree freedoms play out in the cavity, and then we can add Axion to our story. So what will happen because of this Hamiltonian is instead, if you pump your cavity with a laser, so this is again the optical frequency. Not only you're going to see your mode at the laser frequency, you're going to see two other modes. So one is when you emit a phonon because of this Hamiltonian here. So the photon from the pump laser will emit spontaneously a phonon here, and then the byproduct or the other product is another photon. And this outgoing photon will have a different frequency, right? Because of the energy conservation. So that means my outgoing photon will be sitting at this frequency, a lower frequency. This is a right sideband, or what we call Stokes sideband, because this process is called Stokes process. And before I go to the next process, I want to show you the beautiful kinematics here. So we have energy conservation. We have a momentum conservation that I, for simplicity, in principle, you can have a mismatch here where you will suffer from the coupling, have a smaller coupling. So let me assume the optimal case, I have perfect momentum conservation. So I have my second equation here. Then I have my dispersion relations, and for photon, the dispersion is just one, assume speed up. Assume C equals 1 natural unit. And then for the phonon, it comes with the speed of sound, which is 10 to the minus 6 suppressed. So we have 3 set of equations. I can just do the calculation to show you what is the requirement on the mechanical mode that for this process to happen efficiently. And it comes out in one-dimensional set. It comes out very neat and very interesting. So what happens is the mechanical frequency here has to be 2 times the optical frequency. And that means the 2 photons will be back to back. So the incoming photon and outgoing photon will be back, and the phonon is going to take all the momentum out with the factor of 2. And then I can use my simple dispersion relation to calculate mechanical frequency. And it's predicted by a factor of 2 times speed of sound. So that means the mechanical energy here will be almost 10 to the minus 6 suppressed by the optical energy. And this relation that I have predicted you with a couple lines, the calculation has been measured very well by experiments. So like Jack Harris group, they actually measure the mechanical energy here and the theory here, and the experiment agrees very well. So that means what's actually happening in the cavity is exactly this predicted by these kinematics. And this is one possible process. Of course, you can have another possible process, which is absorbing a phonon. So that means the outgoing photon will have a slightly larger frequency. That's the so-called anti-Stokes band. And the kinematic follows almost the same way, just to change one sign here. And eventually you still have the feature where the mechanical momentum is 2 times optical momentum, and the frequency is predicted by a factor of 2 times the speed of sound. So this is what's happening in a cavity, in an optomechanical cavity, which holds both mechanical and optical modes. And just to summarize, these 2 modes will interact with this optomechanical coupling, and the distinguished feature is given by this kinematic. And then if you recall, the problem I was talking about is heloscope is exactly kinematic. So that means this feature of optomechanical coupling, which is kinematics, might help with my Axion process. So now it's time to introduce Axion into the story. So here Axion is nothing fancy, just a kind of a classical background field, which is this A of R here that talks to photon, because we have a Axion photon coupling. At the same time, we have our theory, so optomechanical coupling between the photon, and phonon. So this is the first diagram you can draw down trivially. Basically, a photon Axion converts into a phonon. And actually, the intermediate photon is not doing much, so we can just calculate effective coupling. So I would always like kids to think about this effective vortex, where the coupling is given by, of course, your Axion photon coupling and the optomechanical coupling that can be changed by the fact that Axion is here. But if you work out the mass, the only change is this in this overlapping factor. And that shouldn't be surprising because I said overlapping factor is momentum conservation. Now the momentum conservation is between these 4 guys here. So that means I have my Axion momentum K of A here in my new overlapping factor. But other than that, the optomechanical part is the same. So now I write down my Hamiltonian in case of the creation animation operators. And my Axion field is still classical field, so I'm now quantizing it. With that, actually before kinematics, I would like to say a little bit word about Axion field. So we introduced it's a classical field, but I need the way to describe it. And the first thing I care about is the amplitude of the field, or how strong the field is. Or translating the language we're familiar with is the power spectrum density of the classical Axion field. Turns out it follows a Boltzmann distribution. Just to think about the frequency of the Axion, how that distributed. It's distributed around the Axion mass, well, after a small factor here. And it has a width, which is what we call the Axion line width, that's delta F. And line is given by the quantity I gave you in the very beginning, the velocity of your axion, the axion that in the halo. So the velocity of the axion is 10 to the minus 3 almost. So that means your width here of your PSD of the axion is about 10 to the minus 7 times the mass of the axion or frequency axion. So what that means is you can kind of make an analog as optical modes. The quality factor of the axion flux is like 10 to the 7 quality factor. So that might be a little bit more familiar. So that's the first feature of the axion, the density, the PSD of your axion. And then another feature I want to introduce the kinematics of axion. So the axion diameter is non-relativistic. So that means the momentum is roughly the speed of axion times the frequency where the mass is approximated because you have this distribution, right? Approximate is the velocity times the mass. And the velocity, if you recall, is 10 to the minus 3. So now if I want to compare to what the other two divergence I introduced earlier, the photon here. So the dispersion, what this is, the momentum of the photon is almost the same as the frequency of photon. But if you think about the mechanical mode, the phonon, it's very interesting dispersion because the momentum of the phonon is actually much bigger than the frequency. So you see it's like a hierarchy between the three degree of freedom we are talking about. And because of this interesting feature, the kinematics play out very interestingly. So again, I write my energy conservation now between 4 participants. Momentum conservation, assuming in a simpler case where overlap is 1, and use the dispersion relation I just solved. Then you can solve for what now is a requirement on the mechanical mode. So I don't know why I did it this way. So this is the mode number of your acoustic wave. It's basically the momentum divided by the FSR. So the mode number, again, it needs to match into the optical mode number, which is the 2 times n1, the factor of 2 if you recall. And now I get a correction from axion mass. So here this factor is the axion mass divided by the FSR of your cavity. Take the integer part because we're dealing with integer mode, so I need to take the integer part. So that means it's in order to look at the axion at a different mass, I need to kind of change my mechanical mode accordingly. And that is because I want the mechanical mode to take away part of axion energy. And then the axion mass will be matched into the frequency difference between the two optical modes and the mechanical energy. So what these two equations saying is I can pick my axion mass and then I change my mode accordingly to this equation. And then I can just look at my outgoing photon at a different frequency, and then I'll be able to approach this axion mass. So what this solves is that I no longer need the equation between the axion mass with the size of the cavity, which is FSR here. So that is why in this setup here, we can solve the problem faced by oscilloscope that we can choose our cavity size independent on the axion mass. And then I just play with my mechanical mode in order for the axion to produce the correct photon at the resonance. So this is the first feature, the first bullet point I want to show. Any question on this so far? Okay, so the next feature, then the next is the second feature, which is the rate. Eventually, we care about how efficient this process will happen in a cavity, right? And either the produced signal is strong enough to be seen by experiment. And for that, I first need to identify my signal. And the signal is identified on the frequency space of your optical modes. So this is our original setup where I have pump laser and optomechanical coupling is happening all the time. So I have my two sideband, the Stokes sideband and the mechanical sideband. I know where they are predicted by the kinematics. And what the axion does is it will produce a new sideband. Because the outgoing photon here will have a different frequency compared to either of the photons from these 3 tones or 3 sidebands. And you can do simple energy conservation to figure out the axion mass, tells you how far away the axion sideband is from the Stokes sideband here. Or you can also calculate what is the distance between the axion side with the pump, which is simple axion mass subtracting the mechanical frequency, which is pretty much 2 times CF times the optical frequency. So what basically you're looking for is a new sideband somewhere else than what you would typically say in your optomechanical cavity or optomechanical system. So of course, how do you detect this? That actually depends on the axion mass. Here I'm showing you an example where the axion mass is large enough, such as you see the axion 7 on the far right side of this axis. Of course, we can also think about axion mass, which is very small. A benchmark we put is FSR, the pi-on-L. I think pi-on-L for 1 meter cavity is about microeV-ish. So if your axion mass is light enough, you're going to produce something that is super close to the Stokes band. And in that case, you will have a large background, because I was showing this a little bit over upscale. The Axion 7 is going to be much lower than all these optomechanical bands, which has a much larger coupling because it's not surprised by the Axion photon photocoupling. So once you're super close, you'll be overwhelmed by the tail of this band. So that means you'll be looking for these photons with a background. But if you're far away enough on the right-hand side, you can principally look at the single photon that pops up from the vacuum when there are no photons. So that's why we like to think about two regimes where axion is heavy, axion is light. But either regime, you can just calculate the rate for this to happen. And this is a simple quantum system, so you can calculate rate by simple Fermi-Goldsmith rule, basically just the square of the Hamiltonian. And I would like to show you very parametrically how your rates depends on these participants. The first participant, which is the Axion, that's the tricky guy because he's so small and he's so big. So I collect all the contributions you will get from the Axion. You get energy, mass density or energy from Axion flux, that's this vector here, and you get your coupling also. And you can have a sense of how weak this process is, just plug in the regular, for example, QCD axion band, because there is the relation between mass and the G gamma double complement. So this factor is actually constant for QCD axion. And that constant is super small. It's 10 to the minus 44. So that means if you're not doing anything with this process, your rate is on the scale of 10 to the minus 44. So like there's no way you can detect such a rate. For example, you're like, Optomechanical is about hertz-ish. So you're looking at the rate which is 10 to the minus 44 hertz. Who can detect this, right? So we need to get some help. And the help you can get is from the optical mode and the acoustic mode, because they're going to be a coherent waves. So that means you get an amplitude of these waves, which is quantified by the photon or phonon number. So the obvious thing to do is to pump your cavity with a super powerful laser. So you have many photons here from the pump. So you get a coherent enhancement of the photon number here. That can be a number of the order of 10 to the 10, 10 to the 20 each, depends on this power. So next, you also want to do the same for your phonon or for your outgoing photons. So you want to pump everything, like you want to put the powerful laser here, you want to put a mechanical drive. But what will happen is if everything is in coherent state, like axion, photon, phonon, then you will have a forward process, you will have backward process. They will come with the same rate, so they will cancel out. So there will be nothing happen. So there has to be something from vacuum or go to vacuum. So that means for the remaining progress, outgoing photon and the outgoing phonon, only one of them can get a coherent enhancement to go into rate. So now we have two options. So either we pump our, either we put a laser here. So I populate my final state. Then you get enhancement from the photon population. That's what we call a photon populated case. So basically you have two lasers, you shine two lasers into the system, you populate two photon states, and the phonon will be spontaneously or non-stimulated emitted. And that's the first game. And this is pretty much your rate. And then what you are going to look for is a short noise fluctuation on the probe laser. So there is a laser sitting right exactly where your signal photon goes to pump up. So you will be looking at a fluctuation on top of the laser power that you observe. And that fluctuation needs to be higher than the short noise fluctuation, such that you know it's not noise, it's some signal. So this is the essential heterodyne detection. So we're going to look at fluctuation on your probe laser. And just a side note, then the phonon will just be spontaneously emitted in order to match the kinematics. So the phonon is kind of in the background. Of course, you have a second choice, which is I am now dealing with I'm not dealing with the second laser. I use a mechanical drive, so I can coherently enhance my phonon here. So naturally, I get a phonon enhancement here in my rate. So number of phonons that I introduced in our beginning. And this is what I call phonon populated case. And what happens here is because I'm not putting a laser here. So in principle, the photon that's produced will be produced from vacuum or non-stimulated or spontaneous, I always like to call it. So you will spontaneously produce a single photon from the vacuum. So what that means is I can, in principle, use a single photodetector to look for this photon. And in principle, it can be background free because there was supposed to be nothing if everything is perfect there, and I will be looking at a photon from the vacuum. So that's why, in principle, this can operate as a single photon detection. Except that single photon detector does not care about frequency. So if you put a single photon detector outside your cavity, it's going to receive everything from this photon, everything from the laser, from your sideband. So we need to put a filter there. So we're only allowing photons within this narrow width to go into my detector. So in principle, that can solve the problem of everything else. And that's why this is narrow band, because when you think about single photon detection, think about the broadband detection. But because of this issue here, this is still a narrow band detection. Okay, so now I have introduced the two ways you can operate this. Two ways you can see your Axion signal. Depends either you put another laser there or you put a mechanical drive and use a single photon detector. So actually you will see that these two cases will be useful depends on the Axion mass. So for single photon detection, here it will be most powerful if your Axion mass is heavy, such that your Axion band is far away enough, so it's not so close to these pouches you put there. So they will be most powerful for heavy Axion mass. Well, for this case, it's actually most powerful for lower Axion mass because you have a probe laser there. The probe laser is very narrow, so you in principle don't want a very broad Axion flux to reduce your signal. So I will show you the rich plot of these both schemes, and you will see naturally the first one will go light Axion mass, the second one will go heavy Axion mass. Okay, so now I have my second ingredient here. I have my kinematics. I know I need to prepare how I prepare my system to actively convert the Axion, and I know the rate. Now the last step is how sensitive my experiment will be. That is going to be given by the SNR, signal to noise ratio. And first, I want to emphasize that either scheme is going to be narrowband detection, so I need to do scanning, and it's narrowband for many reasons. I cannot just browse over. Right. So as of time, I could just now I have my SNR, which is just a signal to background, signal rate background rate. And the background will be very different depending on which scheme you are looking at. So for photon public for the case where I have a laser, because that's where my signal is going to pop up. So the background will be mostly the show noise fluctuation of this laser here. That's the first case. For the second case, I have been emphasizing it can be a single photon detection and it should be background free. And then the irreducible background you would always have is the dark count rate of your detector. That you can break. There's a technology threshold there. So we use the dark count rate of the detector as our background. But of course, if you are sharp enough, you know this is not going to be perfectly background free. So several backgrounds that may appear in our Axion sideband are, for example, the leakage of your lasers from your lasers where touches into the Axion sideband, because those are not perfect delta functions, those are Lorentzian. So there will be a tail of the Lorentzian that is in the Axion sideband. But in principle, this can be reduced if you shape your laser better and better. For example, if you filter out your laser before you send it into the cavity, so cut off the tail, and in principle, this can be reduced. And another feature that is interesting is the Axion photon that produced from the Axion process will have a different polarization than photons without Axion. And in principle, you can also have polarization filter. So all these filters together with random numbers, it should be okay to reduce the background down below this dark count rate if your Axion mass is heavy enough, for example, above macro EV. So that's where we cut out our plot for the single photon detection that I will show you because of filtering issue. And some other noises also, you may have thermal noise or have internal noise. And the thermal noise basically tells you that how cool you need to keep your cavity in order not to have a problem here. And actually, it's not too bad if you're talking about the axial mass, which is 10 micro EV-ish, then you only need to keep your cavity to be below 100 millikelvin. But of course, there's the issue that which is nothing, you will encounter later on that I will show you once I show the rich cloud. But and the mechanical noise, I think we think that is mostly relevant for the low frequency case, and there you already have a very large background of shell noise. The mechanical noise is likely to be larger than the shell noise, so that way do not worry too much. So I would say that this thing here is still under investigation. There may be other sources we're now considering, and that will go into this banding proposal as well. I forgot to mention this, which is the SNR scaling. I always like to think about things parametrically. So we say by the end that this case is much better because this is a background-free detection, and it can be taught by the SNR. Because of shell noise fluctuation, we'll put a probe laser there. You only get your routing enhancement from the second laser. But for this case here, you get linear enhancement from both from the laser and from the mechanical drive. So in this case, the SNR is pretty much better. So before I show you the rich cloud, there is one necessary ingredient, but I don't have time to go through. So what this means is basically we have a narrowband detection. So in order to probe axial mass over a certain range, we need to do scanning. And exactly how you scan depends on which axial mass you're looking at. So there's some subtlety because you're convoluting two fluxes. One flux is axion flux with a Boltzmann. The other one is the lasers. And they come with different ways. So by then you need to decide what is your scanning step, depends on exactly what is your convoluted signal. So it's a little bit subtle. I don't have time to go through this. If you have questions, I can answer you. But I do need to show you how our reach is defined because I'm going to show you a line that covers the extended mass range. So I need to tell you that how that line is drawn. Basically, the line is drawn by connecting individual measurements. So here is the axion coupling versus mass. Every time I curve my measurement at a given frequency, I'm going to get the constraint line like this. So I'm going to constrain everything above, and then I move to the next frequency. I choose my system. I take another measurement. It's going to be a second line here, third, and then what I define my rich cloud is by connecting this mass. Of course, there's a problem is how many measurements you can take over a certain amount of time. For 1 year, 10 years. Here I'm showing you some Yale, for example, if I'm in a flat axial mass, I can actually cover 2 nanometers every year, assuming a 1 second integration time. And if you go to higher axial mass, you will be dominated by the axion flux width for the step, and then you will be able to cover about 1 order of magnitude of that axial mass every year. So that's how I define my reach. And exactly how what is the scanning capability. So still one last thing before the rich cloud are numbers. This is a serious thing that we need to deal with our friends here, and we are not making like super crazy assumption apart from the laser power, I would say. So all these numbers are like most of these numbers are their random numbers. For example, optical frequency, the length we're assuming 1 meter, which is variable. Speed of sound is from superfluid helium, and the finesses, so typical finesses you can deal with. And there are 2 key parameters here. One is the laser power, which determines the number of photons. I was showing you everything parametrically with the number of photons. That depends on laser power. I'm going to show what laser power is assumed. And last thing is the phonon number. So it's still an unanswered question. What is the capability of putting phonons in your cavity? How many you can host before you bump into all kinds of problems, which is kind of unknown. But there is one thing you know is you cannot pump too many phonons such that you have too much energy in your material. So if you have too much energy, you will just pull apart the material. So that is limited by this factor here. That's the maximum density fluctuation you can get given by the material. And you will here tell us a number, for example, 1 per million. So we just use that to calculate what is the maximal number of phonons you can host. So that's what we assume for the phonon number, just by calculate the maximum mechanical energy you can host. So that is the last thing that we need to know in order to see the rich cloud. So this is the first case where I have two lasers. So I look at show noise fluctuation on the laser, and you can see the rate actually just go up when the mass is about like 10 to the minus 7 microvolt. And even I use very like powerful laser 10 kilowatt is not good enough because I suffer from the show noise fluctuation. And also the laser power is not as good as that field. So we're not going to beat CD max, for example, and except we can go to lower mass. So this again is not very optimal. We're thinking about what we can do. I can talk more like offline, but that's why we mostly focus on second case, which is a single photon detector background frame. So the line that you see obviously can touch the QCD line is the lower dash line. The reason we put it to be dash is because we're assuming very low dark count rate, which is millihertz. So millihertz is not too bad for single photon detector. You can find something like this, but what that means, you need to keep all the backgrounds, all the possible noises below 10 to the minus 3. And that we need more careful investigation. It depends on how low temperature you can keep the system, how you can stabilize the system against tensile noise, and how good your filters work. So it's kind of not immediately clear. We can keep everything down to millihertz, but if that's possible, then we can think about this line that will touch the QCD axion. Of course, another thing you see stand out here is the laser power. So we're assuming very strong laser power. That actually is the laser power LIGO uses. LIGO is very similar to mechanical cavity, unless except the cavity is empty. But the LIGO has the same kind of mirrors, have the same kind of setup. So they are using 10 kilowatt laser, and that's where we got this number. So with these two K parameters, the dark count rate and the laser power, that's where we're sitting at if we can do single photon detector. And you'll notice that I cut off the diagram at 10 to the minus 6 micro EV Axion mass because we are not sure how well we can filter the backgrounds below this, as reasons I was telling you earlier. But of course, if we can have super powerful filters, we can have things under control. You can push down to lower axial mass. You see the rich curve actually continues. There's nothing to cut it down. Okay, so that's the rich that we think most promising. And I think that will basically conclude my talk. There are benefits to evolve phonons in my system. It helps with kinematics. It helps with the rate. And of course, exactly how well this can do, how well, like if we are going to test QCD axion, depends on the realistic experimental numbers. And then there are serious questions to ask. For example, like filtering thermal model, like how the heat on the mirror transmitted into your bulb. And there's something interesting about strong coupling regime because with so many number of phonons and photons, we'll be talking about multi-phonon photon interaction, which is strong. Then you might have secondary sediments and things like that. And of course, this system may be possible to do progression of it. That's something we're thinking about. And last, we need a concrete experimental proposal. So that will conclude my talk finally. And thank you so much for.
Okay, yeah, thanks for a great talk. We have some time for questions. So first I'm going to see if anyone on Zoom has any questions. Okay, it doesn't look like it. So yeah, anyone in the room?
Yeah, thanks. So maybe I'm understanding it incorrectly. So your axion signal as a photon can actually go anywhere, right?
It's predicted by the axion mass. So if you're going to put a constraint at a given axion mass, that tells you where the photon is going to pop up.
But in terms of, for example, scattering angle, it could go like three-dimensionally.
Good. So that's a very cool question because so first of all, we're assuming one-dimensional configuration. And of course, your axion may come with any angle, even you shoot your lasers back to back, right? Or mechanical one dimension. But the key feature here is the axion momentum is very small because what gives you the angular dependence is your axion momentum, right? And the momentum of the axion, which is where I have that axion mass times 10 to the minus 6. So you have a super small momentum, and if you do the calculation for the kinematic, I can't show you like exactly, but if you do this kinematic calculation, you see actually the axial momentum decouples from all the equations. So it's not going into the equation. So the axial mass does not, axial momentum does not change the kinematics. That means doesn't matter where is your axial momentum, which angle it is. Of course, in principle, even it's small, but because the axion dark matter comes in different angles over the day. So this experiment will have a data modulation, like directional information on axial mass, but it will be very small. We did the estimate, it's like kind of very small because the axial momentum is very low.
Okay, I guess I'm asking a more practical question, like, do you need to populate single photon detection around your 1 meter cavity, like all around in a pixelated way?
No, because according to the kinematics, your outgoing photon will be aligned with your incoming photon.
Okay, that makes sense.
Right. I'm not showing the correct equation.
Any other questions?
So I was going to ask something related to that, which is, so if you do make your cavity longer, you're going to reduce the geometric acceptance for the helioaxion, won't you? I mean, because the angle will be less if you make it longer.
So I guess it's a kind of same answer, and don't know if satisfying enough because exactly where which direction the axial momentum is doesn't matter. So basically, axial momentum can be neglected in the whole process. What matters is the energy of the axion, and the energy doesn't have a direction. So either your axion comes in this direction or comes in this direction, it doesn't change the rate, it doesn't change the kinematic matching.
Okay. I can say that slightly differently. So I don't imagine the axion entering the cavity at all. So it doesn't have an acceptance angle. It's just in my head.
Angle on the up point.
No, not on the axion at all.
No, not on the axion, but on the phonon.
On the phonon, yes, but that we are actuating by ourselves. So, or
Yeah,
even
okay.
if image, yeah.
Yeah, so very nice talk. I was wondering about the directionality. It's actually sad you don't get the free momentum playing a role here, so that's too bad. But like, what is small? Is that like 10⁻⁶ or?
10⁻⁶ times your axial mass, and the axial mass is only we are sitting on. For example, if we're talking about the optical frequency, about terahertz, that's like about EV, electron volt. And that's also the momentum of your phonon, because there are 2 times of the optical momentum. So we're talking about 3 momentum, which is about EV. Well, your axial momentum is about axial mass, let's say micro EV times 10⁻⁶.
Yeah, so in terms of like modulating counting rate, it's going to be also like counting rate modulations of 10⁻⁶.
Right. So actually, in the calculation, the modulation comes in this factor, the overlapping factor, because that's your momentum matching. And basically, you're looking at the time modulation on this factor, and it's a sinc function. You're looking at fluctuation of sinc function around 1, which is a small fluctuation.
Yeah, it's not going to help with the dark rate.
Yeah.
And so so I know there's dark rate in the single photon detector. What about mechanical? We talked about mechanical noise. What about the mechanical dark rate? I mean, maybe this is also for folks.
So that also can be filtered out because it's not in the right frequency.
Yeah, but like, is that really true when you have a 10-meter object that there's no micro EV fluctuations at this frequency? I know it's a very small phase space, but
Can we filter it out? That's a good question.
Yeah.
We don't know. So right now we need something like 44 orders of magnitude. The best we have done so far in YSB or Wright lab is 12 orders. But the best that other people have done is around 20 something.
but that's for the photon.
That's for the photons and also phonons. So then we remove the background, so to speak.
But how is it? I mean, you have some thermal occupation, I guess, of phonons, at least you can pull that away. But is it known what the mechanical occupation of phonons is? I mean, like in the dark matter detectors, right? I mean, there's also these phonons, athermal phonons, people don't really understand the source of it. Like, does anyone understand the source of athermal phonons at 100 like megahertz, like micro EVs? I mean, it'll be interesting to see. But,
Yeah. I agree with that.
Okay, thank you.
Oh, also, just quick question. You said it is sad because The modulations are a signature of something?
Oh, yeah, they're exactly the signature. you
I
want.
see, yeah,
So let's do that.
yeah, that's what I'm looking for. I see.
Does the helium have to be super, super pure if you're gonna put 10 kilowatts in it? And not get any, phonons coming off dirt?
So, yeah, the idea is at least the helium is pure by definition because the impurities go and stick to the walls of the fridge. But we have had issues in our other experiments where the helium is just floating in air. And if there are no containers, then the impurities just get trapped in the floating helium drop. But not here, because over here it's going to be contact with things.
I had a question about single photon detection. So you talked some about how you would filter the single photon detector, but what do you propose to use as a single photon detector in that frequency? Because I know different ones are better for different frequencies of light.
That is some answer I really don't know. Exactly which type, I don't know, but I think last time we talked to people, they say you can find a single photon detector in that frequency. But exactly, for example, what is realistic Dark-on rate, what kind of single photon detectors that I really don't have answer for, I'm sorry.
So what's the frequency?
So it depends on the axion mass, but pretty much you're looking at terahertz with the correction from the axion mass because the optical, yeah.
Yeah, these are optical photons. Yeah.
Right.
I see. I missed that the photon frequency was much higher than the
Right,
axion
right,
mass
right.
because
Yeah.
I'm used to thinking of it as a frequency at the axion.
Yeah, good. So it's like optical photon plus the axion mass.
I see this. Yeah, that's much easier to do with the standard single photon detector. That makes more sense.
Okay, any more questions? No? Okay,
Can I have one question?
yeah, sure.
So why helium optomechanical system is needed?
Good. That's the question we are actively discussing. So we start with superfluid helium because the motivation that it can have very good optical and acoustic fitness. Because like the fitness matters here. Like it matters how many photons you can pump into there. If you look at the final very long equation I didn't even mention, you can see the fitness actually affects the rates, right? But then at the same time, you can see other factors here. For example, speed of sound, that's actually constant. If you put everything together, maybe it's easier to like the speed of sound and the dielectric will be better with other material because superfluid helium is not so polarizable. But then at the same time, you need to think about how can you reach the same amount of acoustic and optical fitness with other material. So that's a compromise, but like kind of need to balance between. That's something we're actually discussing. Of course, there's another factor according to our friends. Superfluid helium is much more expensive. So maybe we can look for cheaper materials. So it's really goes into the experiment proposal phase. What is the best material to use? But I guess the concrete thing I can say is superfluid helium is good in the sense that the finishes are good. But then you have other factors here.
And the other is how hard we can drive it. So the M phonon.
Right.
For helium, it just never goes nonlinear. For the other guys, reach or hit nothing nonlinearity or some of the nonlinearity pretty soon.
Right. So that's kind of the strong. I call it differently. I call it strong coupling regime, but it's a non-linear regime as well. But you'll need to do it as well.
Okay, well, if there are no more questions, let's thank you.